Okay, now in this lecture we will continue the discussion of the previous lecture, that is the discussion on wave analyzer. Now in the case of the wave analyzer, we have seen that it is a classification, extended classification of signal analyzer. There is different type of signal analyzer, that is first one is maybe the spectrum analyzer, second one it is maybe wave analyzer, and third one it is maybe distortion analyzer. Both three are important in their respective applications related operation. Now in the case of the wave analyzer, we have discussed the frequency selective wave analyzer. That means we want to constant only the audio frequency range signal for which we want to measure the amplitude of a particular frequency signal, that we are interested for now. Okay, so frequency selective wave analyzer, the first application of frequency selective wave analyzer or classification of this frequency selective wave analyzer, that means it is operate only in the audio frequency range, and the audio frequency range is extended only 20 hertz to 20 kilohertz. That is the range of the audio frequency, and for that range we are only apply the frequency selective wave analyzer. Okay, and next is your heterodyne wave analyzer. Now when the frequency range increases, then this frequency selective wave analyzer may not be suitable to isolate the different frequency and extract the amplitude of that frequency. That instrument is not suitable for that purpose. So for that reason this heterodyne wave analyzer is used. Now in the case of the heterodyne wave analyzer, the difference from the previous one is that it is operate in a higher frequency range. As you can see, it is written that it is in the megahertz range. Okay, so the frequency amplitude that we require, the amplitude of the different frequency component, if the frequency component is higher than the audio frequency range or maybe limited to 20 megahertz range, then we are using this heterodyne wave analyzer. Now the principle of heterodyne principle is actually used in communication engineering. Now in the case of the communication engineering, you might have seen that this type of block diagram explanation, that heterodyne receiver. In that case, the main principle is to mix the frequency or shifting the frequency from one range to another range by mixing with a local oscillator. Okay, so the heterodyne principle is actually says in a very layman term that the heterodyne means mixing the original frequency with a different frequency one to change the original frequency range to another frequency range. That is very easy to process. That is the main principle or the advantage of the heterodyne principle. Now in the case of the heterodyne wave analyzer, there is a very simple block diagram. You can see, you can refer to this website, and I am extracting the information from that website for a better understanding, a very easy understanding rather than that is this is the attenuator. Signal is fed from the actual signal that is fed to the input attenuator, and the attenuator function is to compress the signal. If the signal amplitude is too large, it is actually compressing to the instrument range. Okay, now as I have said in the previous, that the range of the heterodyne wave analyzer may be in the megahertz range. Okay, up to 20 megahertz. So the mixing principle happens with that there is a local oscillator. Okay, so in this local oscillator, the frequency supplied may be 30 to 48 megahertz. Okay, and this is your Fox mixture. The principle of heterodyne, as I have said, that mixing in the main principle of the heterodyne wave analyzer. So 0 to 18 megahertz may be your raw frequency signal that we want to analyze, and it is mixed with a local oscillator. That frequency range local oscillator is actually generating a fixed frequency. Okay, that frequency range is from 30 to 48 megahertz. Depending on the input signal frequency, that frequency is selected. Okay, if the input signal is 18 megahertz, then the local oscillator frequency must be set to 48 megahertz. Okay, so that we can get the 30 megahertz fixed output signal. That is the main aim of our mixing circuit. Okay, so that is, first one is input signal is fed to the input attenuator. Next, the input attenuator, after the raw signal is from 0 to 18 megahertz, and from this 0 to 18 megahertz signal we want to transfer that signal into 30 megahertz signal. Okay, that's why we are mixing the signal with a local oscillator. And the local oscillator, the simple term, if we multiply these two signal and goes to the Fourier transform, then you can see that this cos plus b into cos a minus b. That means both the signal frequency are subtracted. So that's the principle of the mixer. So we have get a 30 megahertz fixed output signal transfer. This signal is transferred to that frequency range. Okay, then there is a IF amplifier. This is also communication engineering instrument. This IF amplifier, after that there comes case of the second mixture converting a very low frequency range. Okay, so our actual signal is converting to a very low, again mixing the signal 30 megahertz fixed signal with a near about 30 megahertz crystal oscillator. So after plus minus it is near equal to 0 megahertz, consisting the signal or outputting the signal near equal to 0 megahertz. Okay, so this is the active low pass filter. So active low pass filter actually passing the signal up to 1.5 kilohertz. This 0 megahertz is actually the theoretical term. It is not actually 0 megahertz all the time. There must be some sort of component which ranging up to this range. Okay, so up to this range the low pass filter is passing the signal, and then the meter circuit is measuring the amplitude of that particular frequency range signal. So that is the main operating principle of the heterodyne. And from the this circuit you can also see this is the same circuit. 1 minute. And you can see that this is your input signal and this is your attenuator. Attenuator is actually amplitude control, it controls the amplitude of the signal. And next is your input amplifier. If the this is controlling the amplitude of the signal. Next, this is the mixing happens. This signal range is from 0 to 18 megahertz, and this oscillator frequency is 30 to 48 megahertz, generating a signal that is difference of this 30 megahertz. And this mixture frequency fixed oscillator in 30 megahertz. From this output is near equal to 0 megahertz, not actually 0 megahertz. That is not possible for the mathematics or the theoretical term that we are getting the 0 megahertz output signal. That is not possible. That means it is a low frequency content signal. Okay, that is the main principle, low frequency content signal. That's why we are having a low pass filter, active low pass filter here. Okay, then we are amplified, then we are meter measuring the amplitude of the signal. So that is the main principle of your heterodyne wave analyzer. And these are the some applications. It is used in electrical measurement, it is used in sound measurement, it is used in vibration measurement. Okay, so different purpose and different section it is used. Okay, now we will discuss harmonic distortion analyzer. Now, what do you mean by the harmonics of a signal? Now, harmonics is defined in the case of the signals and system term. That suppose this is your sine wave, pure sine wave. Its frequency may be 50 hertz, lab generated waveform. But in a practical circuit, whenever this signal is fed to an amplifier and get the output signal out of the amplifier, or this signal pass to a load, obviously non-linear load, not linear type load, just like resistance, capacitance or inductor, passed to a nonlinear load, then this waveform, after passing this, the output getting is distorted. Distorted means the output composed of a fundamental frequency, that is the pure sine wave, in this case 50 Hz, plus multiplier of this fundamental frequency. That means if the fundamental frequency f, then we get the output waveform summation of this 2f plus 3f, like that. So we didn't get the exact replica of the input signal at the output. In a most elaborative term, suppose this is your amplifier. Now the characteristics of the amplifier is does not change the frequency of the signal. Okay, the good amplifier does not change the frequency of a signal. Suppose this is your sine wave and this is your amplifier, any type of amplifier, maybe power amplifier. So the amplifier output is just like that. That means is amplitude it enhanced. That is the purpose of the amplifier. Okay, if this frequency is 50 Hz, the output frequency must be 50 Hz to get a faithful reproduction of the input signal. Okay, otherwise if the output signal is composed of 50 Hz plus the other frequency, due to the different circuit component distortion, then we can call that the output of the get, in the case of the radio, we get the distorted sound. But if we get the pure output like that, which is composed of only the fundamental frequency as in the input, then we get the we didn't get any type of noise at the output. So noise is generated due to harmonics, and harmonics is cannot be avoided. It is inherently produced in the circuit. So that's why the analyzer comes into picture. That means, as I have said, that we cannot get the pure output out of the amplifier or out of the any electronic circuit. So the output is composed of a fundamental frequency which is given at the input plus the different frequency component. Now as this cannot be avoided purely or completely from the output of the amplifier or any kind of circuit, then the study of this noise or the distortion is studied with the help of this distortion analyzer. That's why distortion analyzer comes into picture. It actually measures the how much this distortion component is actually the ratio of the total power of the fundamental power divided by the total power. If the total power of the distortion is higher, then it didn't get any type of sound. The noise is actually dominant in that case. Okay, so that is the main purpose of the harmonic distortion analyzer. As distortion cannot be avoided in the circuit, that's why distortion analyzer or the measurement of the distortion analyzer comes into picture. That means we have to measure the distortion and must have to employ certain kind of extra circuit to eliminate this type of distortion. Hope you get it. And in the next figure I am giving you the FFT, Fourier transform of a pure sine wave. This is suppose the pure sine wave, as I have said in the previous lecture, 50 Hz pure sine wave. And if you get the Fourier transform, okay, of this signal, then we get a spike at 50 Hz. Whatever may be the frequency of that signal, we get a spike at 50 Hz. So that is the pure sine wave or the fundamental waveform Fourier transform without distortion. Okay, now if the distortion is happens, then the suppose this signal is fed to an amplifier and the amplifier output is like that. Now you can see that this amplifier output, just seeing the time domain analysis, you cannot know what type of harmonics are present in the signal. That's why Fourier transform comes into picture. It actually exposes the inside frequency component, okay, in its frequency domain. So that's why this is the fundamental frequency f1. You can see that this is the fundamental frequency which has the highest amplitude, obviously. And next this f2, f3, f4, f5, f6 diminishing amplitude. That means these are the all the distortion. If the distortion component is higher like that, then you didn't get the original sound. Original sound is totally suppressed by this harmonics. These harmonics are undesirable, but they are inherently produced into the circuit due to the different circuit components. This cannot be avoided totally. Okay, so after getting the Fourier transform, we get what type of distortion is present within a signal, and with the help of circuit, different circuit, we are measuring the this component power to this component power. Okay, so that we can measure what type of, how much distortion is present in the our circuit. Okay, so different type of distortion is happens. First one is your frequency distortion. Okay, frequency distortion means different type of frequency is going to present. Phase distortion, apart from the original phase that is present in the signal, the phase distortion actually happens the energy storage element in the system. Different energy storage element causes the phase distortion. Energy storage elements mean the capacitor, maybe your inductor, and that causes the significant phase distortion in the output circuit. Next, amplitude distortion. Amplitude distortion means whatever may be the amplitude you are getting, the output, desired output cannot be get, and we may get this type of signal like that. So this is your amplitude distortion. And next is your intermodulated distortion and crossover distortion. Crossover distortion is happens in the case of the heterodyne circuit or the mixing circuit, and also the intermodulated distortion. These two distortion is actually happens in the case of the communication circuit. Okay, so next, total harmonic distortion. Now the total harmonic distortion is actually may be simplified. In the case of the simplified term, it is defined as that it is a measure of the harmonic distortion present in a signal and defined as the ratio of the sum of the powers of all harmonic components to the fundamental frequency power. Okay, so that is the main term of calculating the total harmonic distortion. I am giving with a mathematical example that will be much simpler. So that means your fundamental energy is E1. Okay, your fundamental energy that is present 50 Hz. In the case of the 50 Hz signal, that is due to the 50 Hz signal the energy is E1, but due to the different others frequency component the energy may be E2, E3, E4 like that. Now the distortion component is calculated like that, that frequency component power to the total fundamental power, that frequency component power to the total fundamental power, like that. And total harmonic distortion is calculated just by like this ratio root over d2 square, d3 square, d4 square, like that. Okay, so as d2 is E2 divided by E1, so the expression may be total harmonic distortion expression is like that. Okay, this is the expression, and in the mathematical term this is the percentage harmonic distortion. And in the case of different D, in the different D, that is divided by E1. Okay, E1 is fixed, that is the fundamental power. So this is the overall total distortion. Next is your circuit representation. In the case of the circuit representation, what we are going to calculate, we are try to calculate the total power of the output. Suppose this is your amplifier, this is your input sinusoidal signal, pure sinusoidal signal, and after the amplifier the sinusoidal signal is getting distorted. That means different frequency component comes into picture in addition to the fundamental frequency. So what we are trying, we are only require this fundamental frequency power. So we are just here calculating the total power of this waveform divided by, after removing the F1, this power. After removing F1, that means after removing F1, the total, what is the total power? That means the distortion power that is calculated. Okay, so that is the main of this aim of this circuit. So I am again repeating. Suppose this is your amplifier. This is your amplifier. Okay, we are giving a sine wave like that, and after the sine wave, this sine wave is composed of the fundamental plus others frequency component, that is the harmonics. Okay, so here in this circuit we are trying to calculate this total power divided by power of the waveform, this waveform, after removing the fundamental frequency component. After removing the fundamental frequency component, we are getting the distortion power. So that ratio is calculated, and depending on the ratio we can measure how much distortion is present in the circuit. So in the circuit, this is a very simple circuit. You can see that this is the signal source, this is the amplifier under test, this is your notch filter. So after the amplifier, from the amplifier circuit, the whatever the output waveform is being generated, that is composed of fundamental plus the distortion. Distortion means harmonics. So that is measured by this indicator. Okay, and after the waveform is passed through this notch filter, the main aim of the notch filter is to remove the fundamental frequency. Okay, so remove the fundamental frequency. After removing the fundamental frequency, after positioning it to 2, we are getting the power of the harmonics only. Okay, so harmonics divided by fundamental plus harmonics. So we are getting what type of, that must be less than 1. So very less than 1 for a proper working of the circuit. So in this circuit, through this circuit, we can easily measure how much noise or how much distortion is present in the signal. Okay, so you study this circuit. This circuit is only used to measure the ratio of the harmonics power divided by the fundamental plus harmonics power, and the notch filter is here used to remove the fundamental frequency power. Okay, thank you.